Good evening, and welcome back. Tonight, we are going to turn our gaze away from the earth. We are going to leave behind the noise of the day, the worries of the week, and the lights of the city. We are journeying to the edge of understanding, to the very boundary of what is known. We are exploring the most extreme objects in the universe, places where our understanding of physics is pushed to its absolute limits. Theoretical physicist Janna Levin calls this a journey into black. It is a story of darkness, of time, and of the silent geometry that holds the stars together. So, get comfortable. Adjust your pillows. Close your eyes. Let your shoulders drop. Let your jaw unclench. Let your breathing slow down, deeper and slower. Feel the weight of your body sinking into the surface beneath you. Each breath takes you deeper into relaxation. The room around you begins to fade. The sounds of the world grow distant. You are safe here in this quiet darkness. And now, let us begin. Before we venture to the edge of physics, let us first look up. Imagine yourself lying on your back on a warm summer night. The grass is soft beneath you and the sky above is perfectly clear. The stars begin to emerge, one by one, like candles being lit across an infinite cathedral. Each point of light is a sun. Some are larger than our own, some smaller. Some are young and blue-white hot, others are ancient and red, burning through the last of their fuel. The light reaching your eyes tonight has traveled for years, decades, centuries, some of it, for thousands of years. You are seeing the past, written in light. The universe is patient, and so must we be. Between these stars, in the darkest patches of the sky, there are spaces where light does not escape. These are the places we seek tonight. But first, we must understand how we came to know of their existence. Our story begins, not in a quiet university library, and not in a high-tech laboratory. It begins amidst the mud and the chaos of the First World War. The year was 1916. A German physicist named Karl Schwarzschild was serving on the Russian front. Around him, the world was loud. Shells fell from the sky. Men called out in fear and pain. The earth itself trembled with each explosion, but in his mind there was a perfect mathematical silence. Amidst the artillery, he solved Einstein's equations, and he found something strange. He found a demarcation in space-time, a line in the sand of the universe. He calculated that if you crushed a mass down, a point mass, with infinite density, the gravity would become so intense that nothing could escape it. He imagined an amber energy source crushed to a singularity, wrapped in a boundary. He called it a magic circle. Today, we know it as the event horizon and the point of no return. At the time, scientists thought it was just a fiction, a purely mathematical construct, a ghost in the numbers. Schwarzschild himself would never see his discovery confirmed. He fell ill on the front lines and died within months of publishing his solution. But the mathematics, the beautiful mathematic, lived on. Idea, once born, cannot die. To understand black holes, we must first understand gravity. For most of human history, we thought of gravity as a force, an invisible rope, pulling objects toward one another. Newton described it beautifully. Every mass attracts every other mass, with a force proportional to their masses and inversely proportional to the square of the distance between them. This simple equation explained the motion of the planets, it predicted the tides, it sent rockets to the moon. But Newton himself knew something was missing. How does the Earth know the Sun is there? How does gravity reach across the emptiness of space? He called it action at a distance and admitted he had no explanation. It took 2 centuries for another genius to answer. Albert Einstein reimagined gravity entirely. In his vision, gravity is not a force at all. It is geometry. It is the shape of space and time. Imagine a stretched rubber sheet. Place a bowling ball in the center, and the sheet curves downward. Now roll a marble across the sheet, and it curves toward the bowling ball. The marble is not being pulled. It is simply following the curved path of the sheet. This is general relativity. Mass tells space how to curve, and curved space tells mass how to move. The Earth is not being pulled toward the Sun. It is rolling along the curved fabric of space-time, following the gentlest possible path through a universe shaped by mass. And black holes are places where this curvature becomes infinite, where space itself falls inward. Time moved on. The war ended, and the world changed. But the math remained. In 1939, another mind looked into the void. J. Robert Oppenheimer, a man whose name would later become synonymous with fire, sat down with his student. They published a paper. It is now considered his most important theoretical work. They argued, convincingly, that the complete gravitational collapse of a star was not just a curiosity. It was an inevitable end state in nature. Listen to the words they wrote, like a prophecy carved in stone. When all thermonuclear sources of energy are exhausted, a sufficiently heavy star will collapse. They predicted that this contraction would continue indefinitely. The star would not stop. It could not stop. The gravity would overcome any force that might resist it. And at the end of this collapse, something new would be born, something that had never existed before in the history of the universe, a region of space cut off from the rest of reality. But history has a strange sense of irony, and time has a way of rhyming. On September 1st, 1939, and the very day this visionary paper was published, the world below descended into darkness. The Nazis invaded Poland, sparking World War II. Oppenheimer's paper, his cosmic prophecy, was eclipsed by the shadow of global conflict. Think of it, one science in two fates. The same nuclear physics used to theorize the celestial fusion of stars was harnessed for the Manhattan Project. Science is agnostic. It is a tool for understanding creation or engineering destruction. The sun and the bomb. Oppenheimer would later quote the Bhagavad Gita, "Now I am become death, the destroyer of worlds." But on that September day in 1939, he was still dreaming of dying stars and the quiet darkness they leave behind. The irony is almost too perfect. A paper about the death of stars, published on the day that would lead to the death of millions. But the stars, the patient stars, continued their slow march toward destiny, indifferent to human conflict, burning and waiting and dying. To understand how black holes are born, we must first understand how stars live. A star is a delicate balance, a cosmic tightrope walked between two fundamental forces. On one side, gravity, pulling inward, relentless, patient, trying to crush the star into a single point. On the other side, nuclear fusion, the engine at the star's core. Hydrogen atoms smashing together, releasing energy, pushing outward against the crushing weight. For billions of years, these forces are perfectly balanced. The star neither expands nor collapses. It simply burns. Our own sun had been burning for 4.5 billion years. It has enough fuel to burn for 4.5 billion more. But even stars must die. The fuel is finite. The hydrogen eventually runs out. And when it does, the balance is broken. Gravity finally wins. So, how does the universe create these monsters? How does the light die? Nature finds a way. Imagine a giant star, massive and proud, 8 times the mass of our sun, perhaps 20 times, perhaps 50. For millions of years, it fuses elements, hydrogen to helium, helium to carbon, carbon to oxygen, oxygen to silicon, layer by layer. The star builds an onion of elements, and at its core, it creates iron. But fusing iron is the end. Unlike lighter elements, iron does not release energy when it fuses. It absorbs it. It is energetically expensive. The star's engine shuts down. The fuel is gone. Without the outward pressure of fusion, the star collapses catastrophically under its own gravity. It falls inward. The outer layers rush toward the core at 1/4 the speed of light. In less than a second, the core is crushed to unimaginable density, and then it rebounds. This collapse triggers a massive shock wave, a supernova, blasting the outer layers into space. For a brief moment, a single dying star outshines an entire galaxy, but the core remains. If that remaining core is heavy enough, nothing can stop it. It collapses past the critical point, crushing down into infinite darkness. The physicist John Wheeler gave us a beautiful image for this. He compared the star to the Cheshire Cat from Alice in Wonderland. The star fades from view, leaving behind only its grin. One leaves behind a smile. The other leaves behind only its gravitational attraction. The star vanishes from the observable universe forever. Let us pause here for a moment of quiet. Breathe in, slowly, deeply. Hold it, gently, and release, letting all tension flow away. The universe is patient. It does not rush. Neither should we. Think of the vastness of time. The star we just watched die may have burned for 10 million years. That seems like an eternity to us, but to the cosmos, it is barely a heartbeat. And now, that star has become something else, something eternal. A black hole does not age. It does not decay. It simply exists, waiting in the darkness like a patient guardian at the edge of understanding. Let your body relax even deeper now. Feel the weight of your limbs growing heavier. Feel your thoughts slowing down. You are drifting now like a satellite in a gentle orbit, circling slowly, safely, around a center of perfect stillness. But these stellar ghosts are small compared to what lies in the deep. At the heart of nearly every galaxy, including our own Milky Way, lies a supermassive black hole. These are galactic titans. They weigh millions, sometimes billions, of times the mass of our sun. The one at the center of our galaxy is called Sagittarius A star. It has the mass of 4 million suns, compressed into a region smaller than our solar system. We cannot see it directly. By definition, black holes emit no light, but we can see its effects. We can watch stars orbiting around an invisible point. We can see them accelerating to impossible speeds, whipping around something we cannot see. In 2019, humanity achieved something remarkable. The Event Horizon Telescope, a network of radio dishes spanning the entire Earth, captured an image. For the first time, we saw the shadow of a black hole. It was in a galaxy called M87, 55 million light-years away, a ring of superheated gas swirling around a dark center. That dark center is the event horizon, the point of no return. And it was exactly as Einstein's equations predicted over a century earlier. But a mystery remains. These monsters are far too large to have formed from collapsing stars alone. There simply hasn't been enough time in the universe for them to grow that big. The leading theory, Key, suggests a more ancient origin, primordial seeds. We believe they formed via the direct collapse of massive gas clouds in the very early universe, just a few 100 million years after the Big Bang. It is a chicken or the egg scenario. Which came first? The galaxy or the black hole? We now know the two are deeply connected. The black hole shapes the galaxy, and the galaxy feeds the black hole, a cosmic symbiosis spanning billions of years. Now, imagine you are an astronaut. You are drifting through space, approaching one of these silent giants. We must remember, a black hole is not a thing. It is a place. It is an empty region of space-time, a gravity well more fundamental than matter. If you were to fall in, the experience would depend on who is watching from a safe distance. On your space station, your friend watches you fall. They see your clock slow down dramatically. To them, your image reddens, shifts, and fades. You seem to freeze at the edge of the event horizon, suspended in time forever. Generations could rise and die while your image hangs there. This is called gravitational time dilation. Near a black hole, time itself flows more slowly. A minute for you might be a year for your friend watching from afar, but for you, inside, the reality is terrifyingly different. You feel nothing special as you cross the horizon. There is no wall, no barrier, no sensation of passing through. The event horizon is not a physical surface. It is a mathematical boundary, a point of no return that you only recognize after you have passed it. Inside, space and time swap roles. This is the most bizarre change. The singularity at the center is no longer a location in space. It becomes a moment in your future. You can no more avoid the singularity than you can avoid next Tuesday. Firing your rockets is useless. You cannot fly away from your own future. And for a stellar mass black hole, that future is mere microseconds away. But what happens to your body as you approach the singularity? The answer is both beautiful and terrible. It has a name. Scientists call it spaghettification. Imagine falling feet first toward a black hole. Your feet are closer to the singularity than your head. The gravity at your feet is stronger. This difference is called a tidal force. On Earth, tidal forces are gentle. The moon's gravity pulls the oceans slightly, creating high and low tides. Near a black hole, tidal forces are extreme. Your feet are pulled harder than your waist. Your waist is pulled harder than your chest. Your chest is pulled harder than your head. You are stretched vertically. At the same time, you are compressed horizontally. Your body is pulled into a long, thin strand, like a piece of spaghetti. It sounds violent. It sounds painful. But for a supermassive black hole, this stretching happens so gradually, so gently, that you might not even notice until it is too late. The event horizon is far from the singularity. The tidal forces at the horizon are surprisingly mild. You would cross the point of no return, feeling nothing at all. Only later, as you fell deeper, would the stretching begin, and by then there would be no escape. This brings us to the great conflict, the paradox at the edge of space-time. Stephen Hawking realized something profound. He asked, What happens if you apply quantum mechanics to the vacuum around a black hole? It turns out empty space is not empty, it is a seething quantum sea. Pairs of virtual particles constantly pop into existence and annihilate each other. This happens everywhere in the universe. It is a fundamental feature of quantum mechanics, but near the event horizon, something special happens. If a pair appears at the horizon, one can fall in while the other escapes. To an observer, it looks like the black hole is radiating particles. This is Hawking radiation. It means black holes are not entirely black. They glow faintly with the heat of quantum uncertainty. And over vast stretches of time, they evaporate. But there is a problem. The radiation is thermal. It is random and featureless. It carries no information about what fell inside. If a black hole evaporates completely, all the information about what fell inside, the books, the stars, the astronauts, seems to vanish. This violates a sacred principle of quantum mechanics called unitarity. Information can never be destroyed. If you know the state of a system now, you must be able to calculate its past. The laws of physics must be reversible, but if black holes destroy information, the laws break down. This clash between general relativity and quantum mechanics is the information paradox. One of them must be incomplete. How do we solve this? Physicists have proposed wild ideas. One solution involves fuzzballs. In string theory, the fundamental building blocks of reality are not particles, but tiny vibrating strings. A fuzzball suggests that string theory turns the black hole into a tangled ball of strings. There is no singularity, no event horizon, just a dense knot of quantum strings storing information in their vibrations. Another idea is soft hair. This suggests that black holes have subtle quantum distortions on their surface, like soft hairs, that might store the information. The horizon is not smooth, it is textured with quantum memory, but perhaps the answer lies in something even stranger: wormholes. The leading conjecture is known as ER equals EPR. It suggests a deep connection between quantum entanglement and wormholes. When two particles become entangled, they are connected by a tiny wormhole. It proposes that the entangled particles outside a black hole are connected to the particles inside by microscopic wormholes. The event horizon is not a smooth surface, but a tapestry of quantum wormholes. Information is not lost, it is encoded in the connections between inside and outside, or perhaps the universe itself is a hologram. The holographic principle suggests that the information of a 3D volume can be encoded on a 2D surface. Just like a soup label describes the soup, the boundary describes the bulk. In this view, gravity and black holes are just a projection, and information is never lost because it is stored on the boundary. These ideas may sound like science fiction, but they are the cutting edge of theoretical physics. They are our best attempts to reconcile the very large with the very small. We are searching for a new language to describe this. We are standing on the shoulders of giants. Think of Kurt Gödel, who proved that logic has limits, that some truths can never be proven. He showed that in any consistent mathematical system, there will always be statements that are true but unprovable. Think of Alan Turing, who mechanized thought, leading to the modern computer. He also proved that some questions are unanswerable. Some problems cannot be solved by any algorithm. Now, we need a similar leap to understand the cosmos. Perhaps our current mathematics is simply inadequate. Perhaps we need new concepts, new intuitions that do not yet exist. And we must be humble, so humble. Everything we have ever seen, stars, galaxies, you, me, makes up less than 5% of the universe. The rest is darkness. 27% is dark matter, an invisible substance holding galaxies together. We know it exists because we can see its gravitational effects, but we have never detected a dark matter particle. We do not know what it is. 68% is dark energy, pushing the universe apart. The expansion of the universe is accelerating, driven by a force we do not understand. We have given these mysteries names, but naming something is not the same as understanding it. Maybe we cannot see it because it is hiding in other dimensions. String theory suggests extraspatial dimensions, curled up so small we cannot perceive them. We might be living on a brain, a three-dimensional world, floating in a higher dimensional space called the bulk. The full reality may be far richer, far stranger than the slice we inhabit. The quest for these answers is a deeply human one. It is often a solitary pursuit. Think of Andrew Wiles, who spent 7 years in near-total isolation to prove Fermat's last theorem. For 7 years, he worked alone in his attic, telling no one what he was doing. And then he emerged with a proof that had eluded mathematicians for 350 years. Think of Grigori Perelman, who solved the Poincaré conjecture and then walked away from fame, from a $1 million prize, to live in obscurity. He proved something about the fundamental shape of the universe and then disappeared. They remind us that the pursuit of the answer is what matters, not the fame, not the money, not the recognition, just the burning need to understand. We have built instruments to listen to the universe. We built LIGO, the Laser Interferometer, Gravitational Wave Observatory. It is a facility with staggering sensitivity. LIGO can detect changes in length smaller than 1/10,000th the width of a proton. On September 14, 2015, we heard it. 2 black holes, 30 times the mass of our Sun, had been spiraling toward each other for millions of years. In the final fraction of a second, they merged. The gravitational waves from that collision washed over the Earth. For a brief moment, we heard the universe sing. Black holes have a voice. They ring like a drum, a squeezing and stretching of space-time that we can literally hear. After 100 years of theory, we finally had proof. Black holes are real. Let us now travel forward in time. Not years, not centuries, not even billions of years. Let us travel to the end. In the far future, the universe will grow cold and dark. The stars will burn through their fuel, one by one. First, the massive blue giants will die, exploding in supernovas. Then the yellow stars like our Sun puffing up into red giants before fading to white dwarfs. Finally, even the small red dwarf and the most frugal star will exhaust their hydrogen and go dark. This will take trillions of years, but it will happen. The age of stars will end. What remains? Black holes. In the dark era, black holes will be the only objects of significance. Stellar black holes, supermassive black holes, wandering through the void, slowly growing, slowly merging. But even black holes cannot last forever. Hawking radiation, that faint quantum glow, will slowly drain them. For a stellar mass black hole, this process takes 10 to the power of 67 years. That is a 1 followed by 67 zeros. For a supermassive black hole, it takes even longer, 10 to the power of 100 years, a Google of years. But eventually, even these titans will evaporate. They will release their final photon of Hawking radiation and vanish. And then the universe will be truly empty. No stars, no planets, no black holes, just particles drifting apart forever. Does this ending frighten you? It shouldn't. We exist in the brief window when the universe is interesting. We are made of atoms forged in the cores of dying stars. The calcium in your bones, the iron in your blood, the oxygen you breathe, all of it was created in stellar furnaces billions of years ago. You are literally made of stardust, and someday, billions of years from now, those atoms will return to the cosmos. They will drift through space, perhaps to be gathered up by gravity, to form new stars, new planets, new possibilities. The universe is not wasteful. Nothing is truly lost. Even the information that falls into black holes, if our theories are correct, is preserved somehow, encoded on boundaries, woven into the fabric of space-time, waiting to be read. The darkness is not the absence of meaning, it is the canvas on which meaning is painted. Without darkness, there can be no stars. Without silence, there can be no music. Without the void, there can be no cosmos. So, where does this leave us? Black holes are not an end to knowledge, but a beginning. They are portals to the unknown, where general relativity and quantum mechanics must finally meet. They are the key to the next great understanding, but we must also accept that eventually all of this will fade. The universe will expand, stars will die, and black holes themselves, over eons, will evaporate. The knowledge that our history will eventually be erased is a reminder. It is a reminder to focus on the present, to focus on drawing something beautiful in the sand before it is washed away. The Buddha spoke of impermanence. He taught that nothing lasts forever, and that clinging to permanence is the root of suffering. The universe itself seems to agree. But there is freedom in this. If nothing lasts, then each moment becomes precious. Each breath, each thought, each connection is a gift. You are alive right now in a universe that is still full of light. You can look up at the stars and wonder. You can ask questions that the universe may one day answer. That is extraordinary. That is enough. The universe is vast. The night is deep, and you are safe. Your body is heavy now, sinking into comfort. Your mind is quiet, drifting among the stars. The black holes we have explored tonight are far away. They cannot reach you. They cannot harm you. They are simply there, part of the grand tapestry, part